Welcome back to the Nocturnal Astronomer. Whether you are drifting off to sleep or just looking for something to fill the quiet, these lectures are designed to be exactly that: calm, unhurried, and worth listening to. Just the universe and a little time to think about it. I'm Atlas Reid, your host, and tonight we are going to look at the most powerful events the universe has ever produced. Collisions between galaxies, stars that tear themselves apart in a matter of seconds, black holes that devour matter faster than physics seems to want to allow, beams of energy so powerful they could sterilize an entire arm of a galaxy from thousands of light years away. A cosmic wakefulness. And here is the thing. All of that destruction, all of that unimaginable force happened quietly. From where we sit, the universe looks still, peaceful. The violence is real, but it is so far away and so long ago that it reaches us as nothing more than a faint signal, a soft glow in a telescope, a ripple in space itself. So, get comfortable and let's dive in. Part 1. When Stars Explode. There is a kind of star that spends its entire existence in a careful balance. On one side, gravity is constantly trying to pull all of that stellar material inward. On the other side, nuclear fusion pushes back, keeping the star inflated and stable. For stars like our Sun, this balance holds for billions of years. But for the most massive stars in the universe, stars 8, 10, 20, or even 100 times the mass of our Sun, that balance is always on borrowed time. The fusion reactions keeping them alive are burning through fuel at a pace that cannot last. Eventually, the fuel runs out. When it does, the fusion in the core slows and then stops. There is nothing left to push back against gravity. In less than a second, the core collapses. An object roughly the size of Earth shrinks down to something no wider than a small city in a fraction of a second. The core becomes so dense that atoms are crushed. Protons and electrons are forced together to form neutrons. The result is an object called a neutron star, a ball of matter so compressed that a single teaspoon of it would weigh roughly 4 billion tons if you somehow placed it on Earth. The outer layers of the star, falling inward during the collapse, smash into this newly formed and extraordinarily rigid neutron star. The rebound sends a shockwave outward through the rest of the star. That shockwave is what we see as a supernova, one of the most energetic events a single star can produce. The explosion releases more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. For a brief period, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The light travels outward in all directions at enormous speed, crossing distances we can barely describe. The material thrown off in the explosion forms what astronomers call a supernova remnant. These expanding clouds of gas and dust can stretch across dozens of light years. One of the most famous is the Crab Nebula, the remnant of a supernova recorded by Chinese astronomers in the year 1054. At its peak, that supernova was bright enough to be seen in the daytime sky for roughly 23 days. The Crab Nebula still exists today, still expanding outward, preserving the record of a star's death in the structure of the gas itself. Astronomers can read that history through spectroscopy. Supernovae are productive as well as violent. The nuclear reactions inside a dying massive star and the explosion itself forge heavy elements that did not exist before. Elements like iron, nickel, gold, and uranium are created and scattered into space. The calcium in your bones almost certainly passed through a star that exploded long ago. There is also a subtype called a Type 1a supernova, in which a white dwarf detonates after pulling too much mass from a companion star. These explosions are remarkably uniform in brightness. Astronomers use them as a cosmic ruler to measure distances across the universe, and through them confirmed that the universe is accelerating in its expansion. Part 2. Neutron star collisions. If a supernova is violent, then what happens when two of the objects left behind by supernovae crash into each other is in another category entirely. Neutron stars are the collapsed cores of massive stars. They are small, roughly 20 kilometers across, but each contains more mass than our Sun. They spin rapidly, sometimes hundreds of times per second. Their magnetic fields are so intense they would scramble the molecules in your body from the distance of half the moon. They are, by any measure, among the strangest and most extreme objects in the known universe. And sometimes two of them find each other. When two neutron stars orbit each other, they gradually lose energy through the emission of gravitational waves, which are ripples in the fabric of space and time. As they lose energy, they spiral closer together. This process can take hundreds of millions or even billions of years before the two objects finally meet. Some neutron stars emit beams of radio waves from their magnetic poles as they spin. These beams sweep across space like the beam of a lighthouse. When Earth is in the path of one of those beams, we detect a rhythmic pulse of radio energy. This is why spinning neutron stars are called pulsars. In October of 2017, astronomers detected a gravitational wave signal lasting roughly 100 seconds, produced by two neutron stars spiraling into each other. The signal was detected simultaneously by observatories in the United States and Europe. It was, in real time, the sound of two dead stars colliding. Within 2 2 seconds of the gravitational wave signal ending, orbiting telescopes detected a burst of gamma-ray energy from the same region of sky. Then, over the following hours and days, observatories around the world watched the aftermath glow across multiple wavelengths. An entire planet's worth of instruments pointed at the same event. What that event showed, directly and for the first time, was that neutron star collisions are a primary source of heavy elements in the universe. The collision produced what is called a kilonova. In a kilonova, the violent merger creates conditions extreme enough to forge elements heavier than iron through rapid neutron capture. The glow from that event was consistent with the production of enormous quantities of gold, platinum, strontium, and other heavy elements. Estimates suggested the equivalent of several Earth masses worth of gold alone was created in that single collision. An entire planet's worth of gold forged in milliseconds, scattered into space. Think about that the next time you see a piece of gold jewelry. There is a real possibility, a strong one, that the gold in it was created in a neutron star collision billions of years ago, scattered through space, and eventually incorporated into the cloud that became our solar system. A long pause. The merger does not always leave a new neutron star behind. If the combined mass is high enough, the resulting object collapses immediately into a black hole. The entire sequence, from merger to kilonova to black hole, can unfold in milliseconds. It is one of the fastest and most energetic sequences of events in the known universe. Part 3. The Magnetar problem. Take a neutron star. Give it a magnetic field roughly 1,000 times stronger than an ordinary pulsar, and roughly 1 quadrillion times stronger than Earth's own magnetic field. What you have now is a magnetar. It is one of the most extreme objects the universe has ever produced, and it behaves accordingly. The magnetic field of a magnetar is so powerful it warps the atoms in its vicinity, stretching them into thin cylinders aligned with field lines. No laboratory on Earth can produce anything approaching this level of magnetism. The physics of matter near a magnetar is genuinely different from anything we can replicate or experience. Even the behavior of light changes in the presence of such extreme magnetic fields. This phenomenon is called vacuum birefringence, and it was predicted by quantum physics long before it was detected. It has since been observed near at least one confirmed magnetar, making these objects natural laboratories for physics at its most extreme limits. At distances of 1,000 kilometers, a magnetar's field would be strong enough to affect the iron in your blood. This is not a metaphor or an approximation. The field strength at that range crosses a threshold where biological matter, as we know it, would not function. The magnetar does not care about the distinction. Magnetars occasionally experience what astronomers call starquakes. The crust of a neutron star is thought to be a rigid, crystalline lattice of atomic nuclei. When the magnetic field shifts or the star adjusts its rotation, that crust can crack. The cracks release enormous energy in the form of X-ray and gamma-ray flares. On December 27th of 2004, Earth was struck by the most powerful burst of energy ever recorded from beyond our solar system. The source was a magnetar about 50,000 light-years away, well within our own galaxy. It was not a distant extragalactic object. It was a neighbor by cosmic standards. The initial burst lasted about 0.2 of a second. In that fraction of a second, it released more energy than our sun emits over 250,000 years. The burst ionized the upper layers of Earth's atmosphere, an effect normally associated with solar flares, but caused by something 50,000 light-years away. Had that magnetar been located within about 10 light-years of Earth, the burst would have been powerful enough to trigger a mass extinction. Fortunately, the galaxy is large. Following the initial burst, the magnetar emitted a pulsating signal for about 10 minutes, ringing like a bell in the aftermath of the quake. Magnetars are rare. Only about 30 have been confirmed in our galaxy, though many more may have faded beyond detection. They appear to be young neutron stars, and their extreme magnetic fields are thought to decay over thousands to tens of thousands of years, eventually leaving behind something indistinguishable from an ordinary pulsar. How magnetars form in the first place remains an active area of research. Whether they require an unusually fast-rotating progenitor star, a particularly massive one, or some specific combination of factors is still being studied. What is clear is that a magnetar represents the concept of a magnetic field pushed to an extreme that has no parallel anywhere else in known physics. Part 4. Gamma-ray bursts. If you wanted to identify the single most energetic type of event the observable universe produces, you would be looking at gamma-ray bursts. A gamma-ray burst is a flash of gamma radiation, the most energetic form of electromagnetic radiation. These events are detected somewhere in the sky, roughly once per day, from all directions. The flashes last anywhere from a fraction of a second to several minutes. In that time, a single gamma-ray burst can release more energy than our sun will emit over its entire 10 billion year lifetime. Some of the most energetic ones release in seconds the equivalent output of 10,000 suns over 10 billion years. Gamma-ray bursts come in two broad categories based on duration. Short gamma-ray bursts last less than 2 seconds. These are now understood to be primarily caused by neutron star mergers, like the kilonova event covered in an earlier part. The connection was confirmed directly 2017 detection of gravitational waves from a merger. Long gamma-ray bursts last more than 2 seconds, sometimes several minutes. They are thought to be produced by the collapse of an extremely massive, rapidly rotating star, a type of event called a collapsar. When the core of such a star collapses into a black hole, the surrounding material forms a rapidly spinning accretion disk. Magnetic fields and the geometry of that rotating disk launch 2 narrow beams of energy outward along the rotation axis of the collapsing star. These jets punch through the outer layers of the dying star and emerge into space at very close to the speed of light. The gamma-ray emission comes from shocks within those jets. The key feature that makes gamma-ray bursts appear so powerful is the beaming. The energy is not released equally in all directions. It is concentrated into 2 narrow jets, like the beam of a flashlight rather than the glow of a lamp. Only observers in the direct path of a beam detect the full effect. When one of those beams points directly at Earth, we detect what appears to be an almost incomprehensibly bright event. A gamma-ray burst billions of light-years away can briefly outshine the rest of the observable universe in gamma rays. That is not exaggeration. It is a consequence of geometry, relativistic physics, and distance combined. The afterglow that follows the initial flash has been detected in X-rays, optical light, and radio waves, fading over hours to weeks. By studying these afterglows, astronomers can pin down the exact location and distance of each burst. The most distant detected in recent years came from when the universe was less than 500 million years old. One of the more sobering aspects of gamma-ray bursts is their potential to affect life on other planets. A long burst occurring within a few thousand light-years of Earth, pointed directly at us, could strip away the ozone layer and expose the surface to lethal levels of ultraviolet radiation. Some researchers have proposed that exactly this kind of event contributed to a mass extinction roughly 440 million years ago at the end of the Ordovician period. That remains a hypothesis. What is certain is that our solar system's position in the quieter outer regions of the Milky Way makes us statistically safer than life deeper inside a denser, more active galaxy. Part 5. Supermassive black holes feeding. At the center of nearly every large galaxy in the observable universe sits a supermassive black hole. These are not the stellar mass black holes formed by individual dying stars. Supermassive black holes can contain millions, hundreds of millions, or even billions of solar masses, all compressed into a region smaller than our solar system. The supermassive black hole at the center of our own galaxy has a mass of roughly 4 million suns. It sits quietly at the heart of the Milky Way, pulling in material occasionally and producing flares, but not actively devouring gas in any sustained or dramatic way. At least not right now, not from what we can observe. It was imaged for the first time in 2022 by the Event Horizon Telescope collaboration, a global network of radio observatories functioning together as a single Earth-sized instrument. The image showed a glowing ring of radio emission surrounding a dark central shadow, the event horizon itself, the point of no return. Other supermassive black holes in other galaxies are far less restrained. When one is actively feeding on large quantities of gas and dust, the infalling material forms a structure called an accretion disk. This is a swirling, flattened structure of superheated matter spiraling inward, heated to temperatures of millions of degrees by friction and compression. The accretion disk glows brilliantly across multiple wavelengths of light. Powerful magnetic fields threading through the disk can drive the launch of relativistic jets, streams of plasma moving at close to the speed of light, shooting outward along the black hole's rotation axis in both directions simultaneously, extending far beyond the host galaxy. A galaxy with an actively feeding supermassive black hole at its center is called an active galactic nucleus. The most extreme versions are called quasars. When quasars were first discovered in the 1960s, they looked like faint stars, but emitted far too much energy to actually be stars. The name came from that early confusion. A bright quasar can outshine its entire host galaxy by a factor of 100 or even 1,000. That means a single black hole, surrounded by its accretion disk, produces more light than hundreds of billions of stars combined. The most luminous quasars release energy equivalent to roughly 2 trillion times the luminosity of our Sun. Because they can be seen from enormous distances, quasars serve as some of the most distant objects observable in the universe. They are windows into the early cosmos, active during a period when the universe was young and gas was plentiful. Many of the galaxies we see today once hosted quasars that have since quieted as their fuel ran low. The jets from active supermassive black holes can extend for hundreds of thousands of light years beyond the boundaries of the host galaxy. They carry enormous quantities of energy into the surrounding intergalactic space, heating gas that would otherwise cool, fall inward, and form new stars. The black hole, in this way, regulates the galaxy around it. This feedback process is thought to be one of the primary mechanisms controlling star formation in large galaxies. The central black hole can effectively put the brakes on an entire galaxy's capacity to produce new stars, shaping the structure and evolution of the system around it for billions of years after the active feeding phase ends. Part 6. collisions. Galaxies, for all that they appear as isolated islands of stars, are constantly on the move, and given enough time and gravitational attraction, they meet. Galaxy collisions are not like car crashes in any intuitive sense. The distances between individual stars within a galaxy are so vast that actual stellar collisions during a merger are rare. What does happen is that the gravitational interaction between two colliding systems reshapes both of them completely. Stars that were in neat, organized orbits find their paths disrupted. Gas clouds in both galaxies are funneled inward. The whole geometry of each system is transformed over timescales of hundreds of millions of years. Star formation can be dramatically triggered during a collision. The compression of gas clouds by tidal forces initiates the gravitational collapse that produces new stars. Entire spirals of stars can be pulled into long, curving streamers called tidal tails, stretching across hundreds of thousands of light years and persisting for hundreds of millions of years afterward. One of the most studied examples is a pair of galaxies about 45 million light-years away, sometimes called the antennae galaxies. Their two long tidal tails give the merged system the appearance of an insect's antennae. The collision began roughly 600 million years ago and is still actively ongoing today. Within the chaotic overlap region where the two galaxies are merging, there are thousands of newly formed star clusters, some containing millions of stars each, all created by the compression of gas during the collision. Galaxy collisions are not only destructive, they are generative, producing stars in numbers neither galaxy could have formed independently. Collisions also drive enormous amounts of gas toward the centers of both galaxies, where supermassive black holes reside. This can trigger intense periods of quasar activity as the black holes are fed large quantities of infalling material. Many pairs of active galactic nuclei have been observed in merging systems, consistent with mergers fueling black hole growth. Our own galaxy is on a collision course with our nearest large galactic neighbor, the Andromeda Galaxy. Andromeda is currently about 2.5 million light-years away. The two galaxies are approaching each other at roughly 110 kilometers per second. The collision is predicted to begin in about 4.5 billion years. After an initial close pass, the two galaxies will oscillate, swinging away and then back together before eventually merging into a single large elliptical galaxy over the course of several billion more years. The Sun and Earth will almost certainly still exist during the early stages of this process, relatively unaffected by the large-scale restructuring around them. The odds of our Sun having a close encounter with another individual star during the merger are extremely low, simply because of the immense distances involved. What would change is the night sky. which over millions of years would be increasingly dominated by the sprawling combined light of two great galaxies slowly becoming one. Galaxy mergers are one of the primary mechanisms by which the universe builds its largest structures. Small galaxies merge into medium ones. Medium ones merge into large ones. The massive elliptical galaxies that dominate the cores of galaxy clusters are thought to have grown to their enormous sizes largely through repeated mergers across cosmic history. Part 7. Relativistic Jets Up Close. Relativistic jets deserve closer attention of their own because they are among the most persistent and structurally remarkable phenomena the universe produces. A relativistic jet is a stream of ionized plasma launched from the vicinity of a compact object and accelerated to very close to the speed of light. They appear across several types of systems. Supermassive black holes in active galactic nuclei produce the most energetic jets known. The aftermath of gamma-ray bursts also generates jet-like outflows. Even young stars, still in the process of formation, launch jets, though these are far less energetic than their black hole counterparts. The underlying physics that focuses and launches them shares important similarities across all cases. The leading explanation for what launches and focuses these jets involves magnetic fields. The rotating accretion disk around a black hole has powerful magnetic field lines threading through it. As the disk rotates, it winds and twists those field lines, which then accelerate and focus material along the rotation axis, launching it outward at relativistic speeds. The spin of the black hole itself can also contribute energy to the jet. A rapidly rotating black hole warps the space-time around it, and that warped geometry can extract rotational energy directly from the black hole and transfer it to the outgoing jet. The result is a highly collimated beam of plasma moving at a significant fraction of the speed of light. The plasma within these jets emits radiation through a process called synchrotron radiation. Electrons moving near the speed of light spiral around magnetic field lines and emit energy across a broad range of wavelengths, from radio waves through visible light to X-rays. This emission is what makes relativistic jets detectable from billions of light years away. One of the most remarkable nearby examples is the jet from the giant elliptical galaxy at the center of the Virgo cluster, the same galaxy whose central black hole was imaged by the Event Horizon telescope. The jet extends about 5,000 light-years from the galaxy's center and is visible clearly across multiple wavelengths of light. Because this galaxy is relatively nearby, at about 54 million light-years, astronomers have been able to observe motion within the jet itself. Plasma structures within the jet appear to move across the sky faster than the speed of light. This effect is called superluminal motion it is an optical illusion, not a real violation of physics. It arises because the jet material is moving at close to the speed of light and nearly directly toward us. The geometry of the situation produces apparent velocities that exceed light speed. The illusion is a predictable consequence of relativistic motion, and detecting it actually confirms just how fast the jet material is truly traveling. When a powerful relativistic jet plows into the surrounding intergalactic gas, it forms enormous structures called radio lobes. These are regions of diffuse, magnetically inflated plasma extending for hundreds of thousands or even millions of light-years beyond the host galaxy. One of the largest known radio lobe systems stretches about 16 million light-years from end to end. A nearby radio lobe source stretches about 12.4 million light-years from featured object E2.G53.0412 to a companion galaxy, NGC 7242, made up of a population of stars. The energy deposited by jets into the surrounding environment is extraordinary. It can prevent gas from cooling and falling back into the galaxy to form new stars, shaping the evolution of the entire surrounding region for billions of years. Some models of galaxy evolution depend heavily on this jet feedback to explain why the most massive galaxies stopped forming stars so early in cosmic history. Part 8. The Violence of Starbirth. Not all cosmic violence is about destruction. Some of it is about creation, and the process of making a star is more turbulent than it might sound. Stars form inside cold, dense clouds of gas and dust called molecular clouds. These are the dark patches visible in photographs of the Milky Way, regions dense enough to block starlight behind them. Inside these clouds, pockets of gas can become gravitationally unstable and begin to collapse inward. The trigger can be a passing shock wave, the gravitational nudge of a nearby stellar birth, or simply the slow accumulation of enough mass in one region over time. The collapse, once it begins, tends to accelerate under its own gravity. As a pocket collapses, it heats up because the gravitational energy of the infalling material converts into thermal energy. The collapsing cloud does not fall inward uniformly. It fragments, with different regions collapsing into different protostars. A single molecular cloud can give rise to dozens or hundreds of young stars, forming more or less simultaneously. Once the core of a hydrogen atom is sufficiently dense and cool, it is able to fuse. This is the first sign of life for a star. As a protostar forms at the center of one of these collapsing regions, it is surrounded by a disk of gas and dust called a protoplanetary disk. This disk is both a source of continued material falling onto the forming star and the birthplace of potential planets. The young star at the center is highly active, accreting material and responding to the turbulent environment around it. As the young star accretes material from its disk, it launches outflows and jets of its own. These protostellar jets shoot out along the rotation axis of the disk and can extend for several light years in both directions. Where the jets slam into the surrounding gas, they create bright bow shocks, glowing regions where the jet material decelerates and releases energy. These jets are not merely spectacle. They inject energy and momentum back into the surrounding molecular cloud, disrupting neighboring gas clumps. Depending on the geometry and energy involved, protostellar jets can trigger further star formation in adjacent regions, or they can suppress it, stirring the cloud and preventing it from collapsing where it otherwise might. As a young star clears the gas and dust in its immediate vicinity, it enters a phase of intense stellar flaring. The magnetic field of a young star is tangled and active. It releases enormous flares, far more energetic and frequent than anything our middle-aged sun produces, bombarding the protoplanetary disk with radiation and energetic particles. These flares influence the chemistry of the disk material and may affect the early development of any planetary surfaces forming within it. The environment of a young solar system is, by any measure, a genuinely hostile place. The disk that will eventually form planets is being irradiated from the inside by its own star while it is still taking shape. Long pause. High-mass stars forming in the same molecular cloud add another layer of disturbance. When a star 20 or 30 times the mass of the Sun ignites, the radiation it produces ionizes the surrounding gas for light years in every direction, creating an expanding bubble of hot plasma that sweeps outward through the cloud. As that boundary expands, it compresses the gas ahead of it, which can trigger new rounds of star formation in adjacent regions. The overall picture of a star-forming region is one of nested and overlapping disturbance. Jets, expanding plasma bubbles, stellar winds, and radiation eroding cloud pillars, all playing out over millions of years and producing, in the end, a new generation of stars. Part 9. Hypernovae and long gamma-ray burst engines. We have already covered supernovae and gamma-ray bursts individually, but the most extreme stellar deaths bring both phenomena together in a single event. A hypernova is a term used for the most energetic class of stellar core collapse, associated with very massive, very rapidly rotating stars. The energy released can exceed a standard supernova by a factor of 10 to 100. These events are thought to be the engines behind long-duration gamma-ray bursts, and they represent the deaths of the most extreme stars the universe produces. To understand why they are different from ordinary supernovae, you have to focus on one key variable: rotation. The spin of the dying star changes everything about about how the death unfolds. When a rapidly rotating massive star's core collapses, instead of forming a relatively slow-spinning neutron star or a simple black hole, the collapse produces either a rapidly spinning neutron star with an extraordinarily strong magnetic field, or a rapidly spinning black hole. In either case, the rotation stores an enormous amount of energy that can be extracted. The magnetic field, or the twisting of space-time around the spinning object, provides the mechanism to convert that rotational energy into outgoing jets. Without the spin, there is no jet. Without the jet, there is no gamma-ray burst. Rotation is not a secondary detail in these events. It is the engine at the center of everything that follows. In the collapsar model, the collapsing star forms a black hole almost immediately. The surrounding material is rotating too fast to fall straight in, so it forms an accretion disk, hot and dense and threaded with magnetic fields. Within a fraction of a second to several seconds after the core collapse begins, relativistic jets are launched outward. These jets must drill their way through the outer layers of the still intact dying star. That process can take several seconds to tens of seconds. Once the jets break through the stellar surface and emerge into open space, they produce the gamma-ray burst we detect. The delay between collapse and detection corresponds to the time required for the jets to punch through. The overall explosion also ejects material in a broader, roughly spherical fashion, producing a supernova-like optical display that persists for weeks. Several long gamma-ray bursts have been associated with hypernovae through exactly this two-part detection. A gamma-ray burst followed by a bright, unusually energetic supernova at the same position in the sky. One particularly well-studied example is a gamma-ray burst detected in April of 1998, associated with an exceptionally energetic supernova in a galaxy about 140 million light-years away. That event was somewhat underluminous as gamma-ray bursts go, which made it possible to study in far more detail than typical, more distant examples. The associated hypernova was one of the most energetic supernovae ever recorded, releasing roughly 100 times the kinetic energy of a standard core collapse supernova. The material ejected in the explosion was moving at a significant fraction of the speed of light, far faster than the ejecta from ordinary supernovae, which are themselves already moving at thousands of kilometers per second. The remnants of hypernovae contribute significantly to the abundance of certain heavy elements in the universe, particularly iron group elements and some heavier nuclei. The extreme energies and neutron-rich environments inside these events produce nucleosynthesis pathways different from both ordinary supernovae and neutron star mergers, filling in parts of the periodic table that neither mechanism alone can fully account for. Part 10. The most violent places in the universe. Having moved through one catastrophic event after another, it is worth pausing to ask where these events tend to concentrate. Not all regions of space are equally violent. The places where violence is most densely packed tend to be among the most structurally remarkable environments we know of, and they tell us something about how the universe organizes itself at its largest scales. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain anywhere from a few dozen to several thousand individual galaxies, along with enormous reservoirs of hot gas called the intracluster medium and large quantities of dark matter, all held together by gravity across scales of millions of light years. The gas in a galaxy cluster is heated to temperatures of tens of millions of degrees by the gravitational processes that assembled it over cosmic time. It emits X-rays. Large clusters are among the brightest X-ray sources in the sky, despite being hundreds of millions or billions of light years away. They are violent environments, made visible by the heat of their own assembly. Within clusters, galaxy mergers are common. The cluster's gravity draws member galaxies together repeatedly. Supermassive black holes in the centers of cluster galaxies are frequently active, launching jets that carve enormous cavities in the surrounding hot gas. These cavities, visible in X-ray images as dark bubbles, preserve the record of jet activity from millions of years past. Some of the most energetic single events in cosmic history have been recorded in galaxy clusters. Observations have captured central black holes releasing energy into surrounding gas over periods of roughly 100 million years that exceeds the total energy output of the entire Milky Way over its history by several orders of magnitude, generated by a single black hole. The dense cores of globular clusters are also extreme environments. These compact spherical groups contain hundreds of thousands of stars packed into a region just a few hundred light years across. Stellar encounters in the cores of globular clusters are frequent on astronomical timescales. Stars pass close enough to exchange companions, form exotic binaries, or collide outright. Stellar encounters in the cores of globular clusters are frequent on astronomical timescales. Stars pass close enough to exchange companions, form exotic binaries, or collide outright. The high rate of interaction in globular cluster cores produces a disproportionate number of millisecond pulsars, neutron stars spun up to very rapid rotation rates by accreting material from a companion star over long periods. These objects are products of sustained, low-grade gravitational violence playing out over billions of years, one of the quieter forms of cosmic extremity. Then there are the starburst galaxies, systems undergoing star formation at rates far above normal, triggered by mergers or by the infall of fresh gas. In a starburst galaxy, the rate of supernova explosions can be tens or even hundreds of times higher than in a typical galaxy like the Milky Way, all of them happening simultaneously across the system. This sustained supernova activity drives a powerful galactic wind that can blow gas and dust out of the galaxy entirely at speeds of hundreds or thousands of kilometers per second. One nearby example, sometimes called the Cigar Galaxy, displays a dramatic plume of ionized gas and dust streaming perpendicularly outward from the plane of its disk in both directions. The universe is violent, not just in isolated events, but in a structured, ongoing way. The largest scales of the cosmos have been shaped by these forces,